It begins in silence. No applause, no spotlight, just the steady rhythm of conveyor belts, refrigeration units, and trucks pulling away from slaughterhouses at dawn. What they carry isn't prime rib or filet mignon. It's what most consumers never see: tongues, intestines, stomach linings, and feet. Offal. A word that sounds like rejection, yet powers an entire sub-economy that crosses continents with the precision of a hydraulic system under pressure. Every year, more than 6 million tons of offal move through ports, railways, and cold storage hubs around the world. That's the equivalent of 400,000 semi-trucks, yet almost none of it is shown in food media or public debates. This is the invisible freight heart of global protein trade, and it never stops beating. To understand this movement is to enter a mechanical ballet of perishability and performance. Offal, unlike other meats, is biologically volatile. It decays faster, carries higher microbial loads, and reacts more aggressively to thermal fluctuation. Transporting it is not just a matter of cold, it's a matter of timing, coordination, and precision refrigeration. Each shipment is a race against an invisible clock, where delays measured in minutes can mean financial loss, regulatory rejection, or health risk. To ensure its survival across oceans, offal logistics must function like a naval hydraulic circuit: valves that open and close in synchronization, pipelines that maintain pressure, and sensors that constantly monitor internal stability. One misfire, and the system fails. And that system has evolved. 100 years ago, frozen meat was packed in sawdust and ice blocks aboard steamships. Today, offal moves inside sealed containers cooled with liquid CO2, equipped with GPS and temperature tracking sensors that communicate in real time with fleet control centers. Visualize this transformation. On one side of the screen, black and white images of men in aprons stacking meat on a wooden deck. On the other, a modern reefer unit humming with automated precision, pre-programmed to adjust air composition mid-journey. The contrast isn't just about tools, it's about understanding. Where there was once waste, now there is data. Where there was excess, now there is value. Because offal is no longer just a byproduct, it is an engineered protein stream, routed through an international matrix of demand, infrastructure, and biological control. What's rejected in one market becomes delicacy in another. In China, chicken feet are considered premium. In Egypt, beef tripe has culinary and religious value. These tastes shape an entire logistics infrastructure, designed not around what the West considers premium, but around what global demand truly consumes. Offal doesn't move like meat. It moves like a volatile asset, fragile, essential, and tracked with military-grade logistics. It's time to reframe how we see it. Offal isn't the end of the line. It's the beginning of a parallel economy, silent, specialized, and structurally brilliant. Like ore tailings in the mining industry, once seen as discard, now refined into alloys and rare metals, offal is rerouted protein, rescued by engineering, and made profitable by logistics. And this rescue isn't random, it's systemic, controlled, designed. The question isn't why we transport it. The question is how we engineered such precision for something the world once threw away. Inside every slaughterhouse, there's a countdown most people don't see. It starts the moment the animal is processed, and it doesn't tick, it accelerates. Offal, especially viscera and organ meats, undergoes rapid biochemical change the instant it's removed from the body. Internal heat remains trapped. pH levels drop. Moisture and residual blood create the perfect environment for microbial proliferation. If cooling doesn't begin within minutes, the bacterial load can double in under an hour. The entire export value, the months of feeding, handling, and slaughtering, can be lost before the product even reaches the truck. It's not a logistical delay, it's a microbiological collapse. But the most vulnerable link often lies far from the killing floor. It's at the dock. At the moment when the product leaves a chilled processing room and meets ambient air, just for a moment, 2 minutes at 20 degrees Celsius. That's all it takes to raise aerobic plate counts beyond legal thresholds set by Chinese or Egyptian health authorities. This isn't hypothetical. Rejections happen weekly, costing exporters hundreds of thousands of dollars in lost merchandise, shipping fees, and embargo risks. Even a well-sealed container can be compromised if it absorbs heat during the loading phase. The cold chain doesn't fail in transit. It often fails in transition. And here's where many logistics models fall short. Most are designed around primary meat cuts: beef loins, pork shoulders, poultry breasts. These cuts are thicker, less porous, and more resistant to surface contamination. Offal, on the other hand, is anatomically exposed and biologically delicate. It requires isolation chambers, rapid degassing of intestinal gases, and high-pressure washing systems, all coordinated within minutes of extraction. When engineers design for meat logistics, they often forget that offal isn't just smaller, it's structurally different. It demands an entirely separate operating logic. Paradoxically, more refrigeration isn't always safer. When a cold chamber is pushed beyond its intended curve, trying to chill viscera too quickly, it can cause cell rupture. Livers turn brittle, kidneys lose structural cohesion. A product that passes every microbial test can still be rejected for texture loss, making it unsellable in premium markets. This is the compressor paradox. Cold preserves, but overcooling destroys. Safe transit requires temperature intelligence, not brute force. That's why a refrigerated container for offal behaves more like a cryogenic chamber than a freezer truck. It needs to maintain a molecular balance, just cold enough to halt bacteria, just warm enough to avoid tissue damage. Too warm, and it becomes a health risk. Too cold, and it becomes waste. Imagine it not as a box of meat, but as a biological payload suspended in time by engineered atmosphere. One miscalibration in this thermal equation, and the product is rejected before it even docks. This is the invisible war behind the scenes. A war fought in pressure units, airflow rates, degassing procedures, and microsecond decisions. And it all unfolds long before the product reaches the supermarket. What looks like waste is, in fact, one of the most fragile logistical challenges in agribusiness, where a 30-minute delay or a 2-degree deviation doesn't cause inconvenience. It causes total loss. Before we move on, take a moment to look at the pinned comment below. In the rural heart of Goiás, Brazil, poultry plants operate with the intensity of industrial hubs. Thousands of birds per hour move through precision evisceration lines. But not all of what's processed is destined for domestic plates. Chicken feet, gizzards, hearts, organs that hold little value in the local market, are immediately chilled, packaged, and labeled for export. Their destination lies thousands of kilometers away, Guangzhou, Shenzhen, and other Chinese megacities, where this offal is considered both cultural staple and culinary delicacy. From the moment these parts leave the processing line, they enter a transcontinental logistics system designed around a very specific kind of appetite. The journey is anything but simple. Trucks equipped with dual-temperature reefer units travel from interior states to coastal ports, navigating agricultural corridors, weigh stations, and sanitary checkpoints. Once at port, containers are loaded onto vessels bound for East Asia, where the journey continues through customs, urban distribution hubs, and often live markets. It's a 30-day logistical choreography where temperature control, container integrity, and export documentation must align perfectly. One step out of sync, and the flow breaks. What was meant to be food becomes condemned freight. This trade only became scalable thanks to container standardization. The shift from conventional cold trucks to high-cube refrigerated containers, units with extended height, and advanced airflow design, multiplied Brazil's offal export volume. These containers now come equipped with ozone injection systems that reduce microbial load without chemical additives. As a result, what once required fast air shipping can now be economically transported by sea without compromising food safety. Over a decade, this technology helped triple the country's protein byproduct exports, not through bigger ships, but through smarter containers. But what really drove this transformation wasn't just engineering, it was culture. Chinese consumption patterns, such as the preference for skin texture in chicken feet or the visual quality of gizzards, forced Brazilian processors to adapt. Cooling procedures, cutting techniques, even packing geometry had to be recalibrated to meet phytosanitary and aesthetic expectations. Brazilian cold chain logistics didn't evolve in isolation. They evolved in conversation with foreign culinary standards. Behind every load of offal is a translated negotiation between what's produced and what's desired. Perhaps most surprising is where the cold chain begins. In many high-throughput facilities, cooling starts not after cutting, but at the feather line, before the animal is even eviscerated. Water sprays, thermal pre-chillers, and airflow tunnels begin removing heat as soon as possible. It's a preemptive strategy designed not just to preserve freshness, but to comply with phytosanitary protocols that require immediate stabilization of internal temperatures. The cold chain doesn't start with the product. It starts with anticipation. Think of the entire route as a protein pipeline. The farm is the source. Customs and inspectors are the filters. Ports are the pressure valves. And at each segment, synchronization is essential. If one valve fails, if the paperwork isn't aligned, if a container's seal is compromised, if arrival time misses the port window, the flow is interrupted. In that sense, the offal trade is less a market than a system, less a transaction than a circulation. What sustains it is not just demand, but the ability to engineer for that demand across distance, time, and temperature. This isn't a minor channel in global food logistics. It's a parallel industry built from what others ignore, scaled by precision, and sustained by culture. A trade route made from leftovers, refined, standardized, and kept alive by the cold. It's easy to think of offal as residue, as waste. But in global logistics, what matters isn't the name, it's the function. And the function of offal in this system is to reveal how precision can transform vulnerability into value. Moving offal isn't about avoiding spoilage. It's about designing for fragility, anticipating failure points, engineering a chain so synchronized, so intelligent, that what was once deemed expendable becomes economically indispensable. This is no longer about making use of what's left. It's about building entire infrastructures around what was never meant to survive the journey. Think of a precision planter used in agriculture. Every seed is dropped with millimeter accuracy, every row calibrated, every second optimized for uniform emergence. That same principle applies here, but instead of seeds, the cargo is organ meat, and instead of soil, the medium is refrigerated steel, embedded with microcontrollers, telemetry systems, and atmospheric regulators. Offal exports function like these planters, unforgiving of deviation, precise by necessity. And behind this precision is something far more profound than machinery. It's the application of human intelligence to complexity, not to simplify it, but to master it. In Vietnam, modified atmosphere containers, designed originally for fruit export, have been repurposed for pork organ transport. By adjusting oxygen and carbon dioxide levels during ocean freight, companies reduced spoilage rates by 27% in under 3 years. What began as an experiment became an operational protocol, proving that even fragile biological cargo can cross hemispheres when handled as a living system rather than static freight. This kind of adaptation isn't rare. It's the logic of the entire offal economy, systems built not to move generic products, but to protect dynamic, unstable ones. For logistics professionals, there's a deeper lesson. Secondary flows. What supply chains once saw as peripheral require primary system thinking. Treating offal as a marginal concern leads to breakdowns. But when it's integrated into route optimization software, monitored by SCADA systems, and traced with RFID tags that follow not just temperature, but pressure and humidity, offal becomes a core feature of the network. It becomes a metric of system maturity, because a system that can move liver across the Pacific without incident is a system that can move anything. Picture, in closing, a conveyor belt. but not the one that carries product away to discard. Instead, imagine a belt that splits. One path leads to waste, the other into a labyrinth of sensors, chillers, vacuum sealers, and traceability data streams. That's the system offal moves through, not discarded but rerouted, not rejected but redesigned. A silent stream of protein, engineered to arrive not just intact, but on time, in spec, and in demand. This is the unseen logic that feeds cities, powers rural economies, and stretches the limits of what logistics can handle. Not with extravagance, not with drama, but with precision. And in that precision, a quiet truth emerges. The most complex systems in agriculture aren't built around luxury. They're built around what others leave behind. This is the kind of operation that often goes unnoticed, but once seen, it changes how we understand food, logistics, and engineering. If this silent choreography impressed you as much as it deserves, take a moment to check the pinned comment. There's something there that continues the journey.